Hello, everyone. I'm Murali Emani. I'm a computer scientist at Argonne National Laboratory. Today, I'll be talking about running MLPerf HPC benchmark suite. So this is a benchmark suite which is designed to run large-scale machine learning applications, mostly from the scientific domains, and running them on large-scale HPC systems. So we know that there have been a significant boost in the computing capabilities of different systems. So we have this top 500 list, which ranks the supercomputers based on a HPL benchmark. So this just ranks the systems based on the flops, the maximum flops. So we see that there are diverse systems with varying number of nodes and different characteristics. So there's also a lot of emphasis on running diverse set of applications on these systems. And if you see that most of them are focused at the HPC facilities at the scientific computers, scientific applications. So the applications are also kind of driven by more of machine learning components within them, and there's a lot of focus on the data analysis part too. And we also see that there's the new systems coming soon. So we have like Aurora at Argonne, Perlmutter at NERSC, at Berkeley Lab, and Frontier at Oak Ridge. And these are supposed to push the frontiers of the existing supercomputing capability. And the other highlight is that they come from a different hardware, diverse hardware set. So like Aurora is built with Intel accelerators, Perlmutter is with NVIDIA A100 GPUs, and Frontier is with AMD GPUs. So, and I also said that there's a lot of stress on the machine learning component from the science community. So the systems are getting very good at running the models like ML training and inference phases. And also the applications are kind of driven by the AI models. So they are being replacing the expensive simulations. So we have, instead of the experiments, so we are running more of simulations and surrogate models. We are kind of replacing a part of the experiments. And the HPC facilities or HPC, the supercomputers are trying to aggressively improve that capabilities. And the DOE labs have stressed the need for the AI-driven science in this technical report. So this lays out a vision or strategy for how should the whole infrastructure coming from the applications, the software stack, and the hardware front. So how they have to work coherently for driving the AI for science. So in order to get a more quantitatively analyzing, like how good are these systems in tackling the scientific machine learning problems, so we need good benchmarks. So they need to tackle this emerging and evolving workloads. So we want to have benchmarks which are representative of the realistic use cases. And if you see that the traditional, the workload domains on HPC, so they span a wide variety of science domains, like coming from, say, bioenergy environment, or from particle physics to precision medicine to nuclear physics. So they are kind of, each domain has its own set of challenges and its own set of nature of the problems. And so unlike like traditional HPC, they are mostly driven by the massive volumes of data. Like, for example, if we have, say, a particle physics simulation running, so it generates a very massive volumes of data set. So you should be able to capture that feature. And when we talk about the production applications, which are mostly driven by the industrial workloads, so these scientific domain applications they have distinct features from that. So they are trying to model the complex physics and the structure, and they are focusing mostly on the massive scale simulations and the experimental science. So it's very important for us to have benchmarks which can assess the HPC system performance, and also drive innovation in terms of the methods and the systems. So as I said, so we also need to have these benchmarks which are representative of these diverse target workloads. We should be able to capture the essence of these realistic workloads which should run on these systems, and we should be able to capture those characteristics. And as I also said, so this we also need to push a lot on the system front, where we expose the issues at scale. So the one other questions or challenges is that, so what's the kind of balance between the targeted approach versus the holistic strategies? Like, we're focusing on a specific application versus a kind of a model that we see across different science domains. And there's also lack of good standard established applications. So we don't have a set of good representative applications. And also, there's a lot of effort required in terms of the expensive area of research, and in terms of the resources required too. So as part of the MLPerf HPC group, we are trying to address this challenge, right? So we have this HPC training working group, and it's played by a bunch of different stakeholders, driven by the US DOE labs and the other labs elsewhere, and also from the industry as well. And the bunch of different activities that we did previously. So we released this the first version of our the MLPerf HPC training benchmark suite, and different activities as well in the previous years. Yes. So in supercomputing conference at 2020 last year, so we released our first version of our training benchmark suite and our results, and all the reference implementations are available in the GitHub repo at MLCommons at HPC. So the first the first version of this benchmark suite has two scientific machine learning applications. So one is CosmoFlow. So CosmoFlow is an application it's trying to predict the cosmological parameters from the n-body Cosmos simulation data. So see that this is coming from a cosmology domain, where the goal is to do kind of a 3D volumetric image data segmentation. The model used here is a custom 3D CNN, and it does this regression of 4 different parameters. In times to so we are trying to capture the time to train as the performance metrics here, and the target for the convergence criteria is getting the mean absolute error to the specific value of 0.124. So this model is run for a number of epochs, and till you read this particular target criteria is met. In terms of the volume of the data set, so we have this 3D volumetric data sets, and the total size of this data set is around 5 terabytes. So that's pretty massive in terms of like running this application. And the second application is DeepCam. So the goal of DeepCam is to model and identify extreme weather phenomena. So this is a kind of analytical climate simulation application. And this application has won the 2018 Gordon Bell Prize at SE. DeepCam uses a DeepLab v3+ model. It does a 2D semantic segmentation. And the goal is to classify our 3 classes per pixel. So whether it's coming from a tropical cyclone, or it's an atmospheric river, or it is just background noise. So the target criteria for this application is getting the intersection over union IO value above 0.82. And the data size is around 8.8 terabytes. So if you see that these two applications have a very specific complex model that's being implemented, and they have a convergence criteria that's set based on the targets that we want to reach. And in terms of the data set sizes, so they are dealing with pretty massive data sets in scales of terabytes. So as I said, so one of the unique features of these two benchmarks in this benchmark suite is that Cosmoflow is trained on the volumetric data. It's more 3D data rather than 2D data, which is most commonly employed. And also DeepCam is trained on a pretty massive resolution of the images, like 768 by 1152 pixels, and as a 16 channels per pixel. So these are kind of very unique and very complex than the standard vision datasets that are used today. And also given the pretty massive volume of the datasets, so they exert significant I/O pressure on the systems. In that way, they are going to expose the storage and interconnect performance. So when codes with such data sets are run on supercomputers, so typically they involve a pretty large scale data movement. So most of the systems optimize this data pipelining in a way that they stage the data from the parallel file systems onto node local storage. So pretty much like most of the emerging or existing top supercomputers have this node local storages where you have this data staging phase. The data is loaded from the file systems onto this on-node storage system. So that's kind of improves the I/O efficiency. So, and to capture that particular phase, when we measure the runtime of these two applications, so we also include the data staging time in the reported numbers. Okay. So in the first version of the submission, so we had submissions from 6 organizations and systems, and that includes a very diverse set of international HPC systems. And we also have the submission from the fastest supercomputer, which ranks 1 on the top 500 list. That's Fugaku. And we had both the closed division and the open division submissions. So on closed division, the maximum scale we run is up to 8,102 processors. And in the open division, this has seen probably the largest scale of the submission so far, running up to 16,000 processors in the open division. And also the other innovation that we found in this submission was the first results which used a hybrid mode of implementation. They're using mesh TensorFlow for that. So using hybrid data parallel and the model parallel implementation. And running that at such a massive scale. So all the training results are also available at this website. So this is a quick snapshot of the results table. So the top list shows the closed division times, and the lower one shows the open division time. So if you see that, so this table shows the submitter on what system we are running, and the system configuration in terms of the processors and the accelerators, and the benchmark results in terms of the time to train in minutes. So closed division is mostly kind of a restricted implementation, trying to get a more of towards getting the apple-to-apple comparison, whereas open division is focused mostly on innovating the baseline implementation and trying to see like how far or how best we can improve these two benchmark implementations. So some of the challenges that we observed as part of these exercises was that obviously, when you're trying to scale, for example, Cosmoflow, we're increasing the batch size, so it hits the limits of data parallelism. So beyond a set of, I think, 512 batch size, so it was found to take a lot of time, or there's a lot of variability in terms of the number of epochs to converge. So we see that there's kind of the stochastic nature of the applications that are being exposed when you're running at large scale, and also by varying different the hyperparameters. And also the convergence for DeepCam was observed to be sensitive to LRDKs. So what we're trying to do is trying to address these in the subsequent implementations, where we do more rigorous hyperparameter implementation even for the baseline references. And other challenges we also encountered was now we are running these codes, or the submitters are on the large scale system. So so these supercomputers are high in demand, right? So they're running a lot of the real world and simulation codes, and so it's very hard to find the number of the resources that are required for running these tasks. And also we're also looking to encourage more advanced and optimized implementations. So as part of the next step, so currently we are working on the next round of submissions. So we are working to, the aim is to publish the results at Supercomputing this year. So some of the additions or the changes that we are addressing currently is improving the existing benchmark suite. So we have these two applications, CosmoFlow and DeepCam. We are trying to address some issues in those two reference implementations. And also we're trying to add one or two more benchmark applications, like looking at this the language models coming from the science domain like BioBert, and also looking at something like a graph neural networks, looking at from the chemistry domain. So so there's still ongoing discussions on which benchmarks that we want to include in this suite. And also for the long-term perspective, we also want to include the HPC workloads, also targeting at inference. And there's also a significant emphasis on this. There's a coupling of the AI plus simulation kind of application. So we're also trying to think that we should also be adding an application coming from this coupling AI plus simulation in the subsequent releases. So if you're getting interested in getting involved in this exciting stuff, so we strongly encourage to join the HPC working group. That's all I have for now. Thank you very much.